All right, now can you hear me? No? What about now? Yes, excellent. Okay. Any questions before we get started? Yes, yes. Or yes, you can hear me, or yes, you have questions. I don't know. I'll give it a second. The homework problem, was it supposed to be 226? No. Probably it was supposed to be 726. But we did not cover wear and surface fatigue. And so I'll have to send an announcement out about that, but those concepts from chapter 7, since we're behind, are not going to be due yet. So in general, I won't have a homework section due that I haven't covered, because I think that's ridiculous in general. So any other questions? So yeah, the homework from the sections that we've covered is going to always be due on that next Monday, and so we're finishing chapter 10 today, and so all of chapter 10 will be due on Monday. I also would hope that you can turn in your. Actually, if we go to Wednesday, which we had talked about last lecture, which I still need to send an announcement about, then I will also postpone the homework until Tuesday. I'm sorry, until Wednesday. To give you a little bit more time. So I know that we needed a little bit of time to try to digest the information that's been presented. So I at least like you guys to have a few days so that you can integrate the things that were talked about and have a chance to ask questions before things are due. So any other questions? Is chapter 12 still going to be due on Wednesday? Probably not, because we'll probably go over the first part of spur gears on Monday. Instead of having half the problems due on spur gears and then the other half due, they'll probably come due the same time as test 3. If we presented last time, is there a chance we will be presenting again? So the short answer is yes. The longer answer is we don't have enough time to necessarily get everybody through. We have less students now than when we started, so we do actually have extra time slots where I may call upon someone to give an update. But at least for the second review, we still have at least 5 teams that we have to see their work that haven't presented. So there will be no surprises for this next design review. So no, if you have already presented, you won't have to present. But I will say that I do expect your reports to be updated, and I expect your design to be a lot further along than it was last time. So the updated design report is still due. All right, any other questions before we get started? If you have questions, just post them down there and I'll pause and answer them. But hearing or seeing no other questions in the chat, I'll go ahead and get started. Today is the second of 2 lectures on splines. On shafts. And we gave an introduction to shafts, talked about what they were and weren't last lecture. Today we're going to talk about deflection, how do we transmit torque from one shaft to another, or from a shaft to a hub through keys and splines, how flywheels are designed, what they're used for, and then critical speeds as they relate to natural frequencies, and then just show you some pictures of the different coupling options that are readily available for you to use in your design of shafts. All right, so we are talking about shafts specifically in this lecture, and they can be treated as beams that are subjected to deflection. Obviously, we don't call a shaft a beam, but if we want to find the deflection, we treat it the same way as a beam because we're considering the deflection due to a load, and it's the same as a beam, so there's nothing special there. Calculating the deflection, that's in their transverse direction, okay? And then we treat them as bars and if they're subjected to torsion. Okay, and that's how we calculate the deflection, transverse and torsional deflections. When we need to calculate the deflection in a real design, it can actually be quite difficult because of the different cross sections, different cross-sectional areas, different attachments, and in that case there's an awful lot of software that can be used to simulate that using FEA, but an approach that you can do that's relatively simple, such as using numerical methods and an integration such as Simpson's or the trapezoidal rule, can be used to define the deflection. And I'll show an example of that. This is the same thing that we've seen before in statics, probably mechanics of materials, and earlier in this class. Is angular deflection is the applied torque times the length of the shaft over the shear modulus, which is the equivalent of the Young's modulus, except a Young's modulus is an axial and shear is in torsion, times the polar moment of inertia, or other words, looking at the area moment of inertia distributed away from the axis that runs through the center of the shaft. The ratio of the applied torque to the resulting angular deflection is the stiffness of the bar. Okay, so if we apply a load and we get a deflection, that's Hooke's law that we've seen in the linear case or with springs, and it's the same thing in the torsional case. If we apply a torque and we get some unit of angular deflection, then that ratio is the stiffness. Okay, so it's a measure of how how much the material angularly deforms for an applied torque, and we can rewrite that in terms of our deflection equation if we'd like, and then then we can calculate the stiffness, okay, of a bar from its material properties, G, its cross-sectional area properties, J, and its length, okay? If we have a changing cross-sectional area, as we do in many shafts, then we have to deal with that, and we can deal with that by looking at the deflections that would be experienced from each section of this shaft and treat it as they are springs in series. Okay, so we can have our overall deflection will be the torque that's applied to the shaft over the shear modulus, assuming we all have the same properties. If not, you would distribute that through for the respective properties, and then the length and the polar moment of inertia for each section of the shaft to get our overall deflection from the shaft. We can also look at it treat it as an overall stiffness of the shaft, and then use that as well to get a feel for how the shaft will deflect due to an applied load. This is an example of the shaft that we saw last time, and it walks us through the process, and we go from A to B, B to C, and C to D. So from A to B, B to C, and then C to D, and we look at the deflections from each one of those. We can add them up and get the overall deflection of 0.15 degrees. And then if we want to calculate the deflection, this is the angular deflection. If we wanted to calculate the deflection of the loaded shaft, okay, we can use the singularity functions that we derived in example 10.1a, okay, but we have to, if we want to use this, we actually have to integrate this, okay. So this is the overall deflection, okay, but it's not the deflection as a function of the shaft. And so we can use this equation for a stepped shaft, and you see we have a smaller area here, larger area here, smaller area here. And because it's stepped, that means that the I in the M over EI equation is going to be a function of the cross-sectional area. Okay, and so what can be done is that we can plot it and then just do a numerical integration for each one of the sections, okay, to find both the X and Y components of the deflection. And then we combine those and then get the overall deflection. Okay, we know that we have the boundary conditions that the transverse deflection is 0. At the end where it's in the bearing, and that means that coefficient is 0. Okay, so this is the slope of the beam, okay, which we can find, and then if we integrate it, we'll get an error. And so because we don't know the coefficient when it's integrated, and so in order to find that coefficient, what we can do is just solve it and then see what the deflection is at the end, and then just move the overall graph down. Okay, so if we are looking at the deflection as a function of the shaft, we can integrate that, and then we can see the overall deflection. And in this case, we had loads in 2 different directions, and so we had to get the X and Y deflection. And then if we take the magnitude of X squared plus Y squared, take the square root, we can get the deflection magnitude as a function of the shaft length. And the reason that this is important is because often you may have rotating machinery and closed in housing, and if you get too much deflection at a certain speed, then that machine will crash into the housing. Okay, so I would go back through this and the previous example in 10-2, okay, from the last section, and make sure that you understand what's going on. Okay, so when we need to transmit torque through shafts, we could from a shaft to a hub. Then one way to do that is to use a key. There's 3 common keys: parallel keys, tapered keys, and Woodruff keys. And the ASME definition is that a key is a demountable machinery part which, when assembled into a key seat, provides positive means of transmitting torque between the shaft and the hub. Okay, so if we have a shaft here and a hub that we need to spin around it, then we can often use a key to transmit the torque from the shaft to the hub. Now, the key is more area of the key is usually in the shaft than the hub, although the design guideline is to split the height between the shaft and the hub. So we have parallel keys. These are square keys, low cost, made with made with cold rolled steel, typically with a slightly negative tolerance, so that a 1/4 inch end mill can machine the slot into the shaft, for example. These are recommended for smaller shafts up to 6.5 inches or up to 1 inch if you're using the European standard or ISO. The height is split between the shaft and the hub of the key. So you place the key in, you want half of it to sit in the shaft and you want half of it to slide into the hub. Then you will slide the hub over the key, and then you can spin the shaft and it'll move the hub. If you need to deal with higher loads, you can use 2 keys, one at the top, and then at least 90 degrees you want to rotate that key so that you can transmit more torque. Otherwise, you'll if you have too much torque, you'll cause the key to fail. We'll talk about that in a second. If you have alternating loads, because there's a small tolerance over here in the key, between the key and the shaft and between the key and the hub, and obviously you have to have some tolerances that'll fit in there. If you have a precision application and you apply a positive torque or clockwise torque, and then you go back and you apply negative torque, it's possible that when you apply the opposite direction torque, you have a small delay before you get output displacement, angular displacement. And that difference, that lag in between the input and output, that's what we call that backlash. Okay, you can feel it if you've ever driven an old car and you have a rack and pinion. You turn your steering wheel left and then right, and you feel that little spot in your steering wheel where you're not getting output motion. It's obviously not as big of an issue in some of the newer cars or drive-by-wire or steer-by-wire, but if you've ever driven an older car, you've probably I felt that. And so what people do is they'll put a set screw in, and you can put a set screw in the hub and then put it into the key, and you can do that, or you can actually put a set screw through the side to try to minimize the backlash. We also have tapered keys. They also have constant width, and the height varies 1/8 of an inch per foot that's driven into the hub until it locks. And so what you're really doing is kind of smashing the key in there. The hub itself will have a taper. Okay, and so when you put the key in, it'll slide down that taper, and then it'll seat inside of the shaft. Okay, so it's a way of locking it with friction. If you get your tolerances right, then it'll snap in there and it'll stay in there. Some have gibs, which are little knobs that you can use to pry them out if you need to remove them. and these are held by friction. We also have the Woodruff key, and this is a semicircular key here, okay, of constant width all the way down, and the penetration is half the key height. These are deeper cuts into the shaft with a circular cutter, making the shaft weaker, but putting more area of the key into the shaft. These are defined by the ANSI standard. I'll show you those in just a second. And they have a numerical value where the last two digits are in eighth of an inch, and the leading digits are 1/32 of an inch, and they are the nominal width. Okay, so the last number is the width. Actually, the first number is the length, so I got to fix that. So these are some standard typical values that you might see. What's important is if you're designing a machine, you need to transmit the torque from the shaft to the hub. You have these range of values here, and these are for the diameter of the key in inches, and you can see they're not recommended for keys over 6 inches. This is the metric version, and if you come down here, you can see for a shaft that's 2 inches, you want a 1/2 inch wide key, and if you're going to use a set screw, you want a 1/2 inch set screw, which matches it. And you'll see that the set screw size slightly lags the key width size, except at 1/2 inch. Okay. The ANSI standard for Woodruff keys, as I said earlier, these are the number corresponds to 30 seconds, 1/8 and 30 seconds. Okay, so 8/8 for the last two digits is 1, and 12/32 is 0.375, and that's how we get our key widths, but they would come in the key number. Okay, so you can pick either the standard Woodruff keys, the standard keys, or Woodruff keys to transmit the loads. They're used in a variety of applications. Keys will fail either by shearing, okay, where you rip it in half, or by crushing when you compress them or exceed their compressive yield strength. For shear failure, it's easy. We just look at the force that's applied to half of the area of the key, and it's in simple shear. And so that means that the shaft is going to be on 1/2 the area, and the hub's going to be on the other half of the area, and the stress on that each area is going to be the force over the area in shear. Usually the area that you use for shear is going to be the smaller of the shaft or the hub areas, and that's because that's the area that's going to fail first, because you have the same force over smaller area, meaning you're going to have higher stress. If you have time varying torque, then you're going to have then fatigue failure is possible, and you would have to compute the von Mises mean and alternating stresses. If you had, say, a mean stress with an alternating stress. Obviously, if you just have an alternating stress, then you would be in compression. Actually, you would be in shear, and so you need to take into account those shear stresses with the von Mises equivalent stress, and then calculate your fatigue like that. Bearing failures where the key is actually crushed. Okay, and sorry, over here, this area is actually the part of the key that's subjected to the shear. Okay, so if we go back, it's actually this area is that shear area. Okay, because that's the shear plane between the two surfaces. If we look at the compressive failure, we're looking at this area right here on the side of the key. Okay, so in that case, it's the width times the length, and in the case The bearing failure, it's half the height times the length, and that's the side of the key. And that side, you obviously want to use the minimum of the area that it is in contact with. So usually that's in the hub. And if you exceed the stress to cause it to yield, then you have compressive yield failure. So those are how keys fail. They are also subjected to stress concentrations, as are everything else that has large changes in or cross-sectional area. Okay. Since the keys are subjected to shear, they're typically made from softer, lower carbon, ductile steel. Okay. If you're going to be in a corrosive or marine environment, then you'd want to use brass or stainless. Square keys are typically made from cold rolled bar stock that are just cut to length, and so they're pretty cheap, and they're designed to fail first. As we saw for the standard keys, the diameter of the shaft determines the key width, and once the width is defined, the height is also defined by the standard keys. You can use a straight key, and that straight key can be as long as the shaft, but in general, you want it to be less than 1.5 times the diameter. And this is where the reason for that is because you're going to have twisting due to torsional deflection, and you want to avoid excess twisting so that you don't twist the key out. So depending on your application, you just have to be aware of that, that if you get the deflection and you have a long shaft, based upon the slides we saw at the beginning of this lecture, a longer shaft is going to have much larger deflection, and if you have a key that runs the whole way, then you're going to be twisting the key. And square things don't like to be twisted, and you can cause problems. If you need to add more higher, if you have a higher torque application, you can add more keys as long as you add them at least 90 degrees from each other. Keys are typically designed to fail first, so they're going to be softer than the key seat. And the reason for that is because they're a lot easier to replace than the shaft. These are the stress concentration factors. They're analyzed in the same way that we've done them. There's plenty of resources you can look up, but the point is that depending on the radius to diameter ratio for the key, then you'll get a factor that can be 2 to 4 times. And so what you might do is, you're trying to do a ballpark design, you can just say that the stress is going to be about 4 times higher at the key. Or if you're designing something that's going to be transmitting loads, you can't just assign the shaft. You have to consider how that shaft's going to transmit that load. It's going to use a key, so you can use a value of at least 2 up to 4 for a stress concentration, so that you're multiplying the stress you calculate by the actual way that you're going to use the machine. And that's what's a little bit different about machine design, is other than statics or mechanics of materials, and that is, to make the machine actually work, we have to use real hardware and real components. And so these stress concentrations, even though we can calculate the stresses, we really have to pay attention to them and make sure that we are multiplying the stresses by an appropriate value. And obviously we'd use the limiting stress case of where we expect the part to fail, just like we do in all the other cases for stress concentrations. At this point, I'd like to remind you to read your book. Your book is good. I try to do a good job of making the information more accessible through these lectures, but there's really no substitute for you to kind of get into the material and read and make sure you understand, especially if there's something you don't understand about these slides. So do we have any questions at this point? So I'll just leave it out there for a second. I know we got a little bit of a lag. So the next thing we're going to talk about is splines. And a spline is this right here. So you've probably seen them before. If you ever removed a steering wheel, you might have seen them. If you've ever removed a CV axle from your car, you might have seen them. Or you might have seen them in a variety of different applications. Okay, so splines are superior to keys because they have more area of engagement. The SAE has suggested to use a value of 25% of the teeth that are engaged, which is larger than just a single key. The standard pressure angle, where there's the tangent where these surfaces touch, is 30 degrees. The tooth size is the diametral pitch divided by the tooth depth, which is 2 times the numerator. Okay, so you can read those tooth size values. Their standard pitches between the teeth are 2.5 to 40, and standard splines will have like 6 to 50 teeth. If you look at the length of the area in contact, this is an expression where we can get an estimate of the overall length of the spline that's in contact with the hub, so that we can do the shear analysis. Okay, so if we get that estimate for the overall length, then we can multiply it by pi d over 2 to get the shear area. And shear is usually the limiting case. They can also fail in compression, but because of the materials, shear is the limiting case, and we can calculate the shear for a spline. That is 16 times the applied torque or the service torque that you're designing against, divided by pi times the diametral pitch, that's the pitch to the average between the two, times the length, which is the length that we calculated from this equation. Okay, so even if we have a spline as an application, we have standards for that. In fact, if you go to the machinery's handbook or you go to the manufacturer, the suppliers, they'll often provide guidance on how to calculate these values. So, are there any questions? All right, so now let's talk about interference fits. Interference fits are another way for us to transmit torque. The torque is transmitted through friction. They're also used for locating pins and mounting bearings and a variety of other applications. This is just the general case, particularly for shafts if we're trying to mount something on the shaft. So what is an interference fit? An interference fit is either a press fit or a shrink fit. Press fit is where we have a shaft that's larger than the hub so that we have interference, and the hub is pressed on, and if we maintain stresses that are below the yield stress, then we don't plastically deform the hub or the shaft when we join them, and we can get them to seat inside of each other. They get the shaft to seat inside of the hub, and then use friction to hold them together. So if you've ever tried to remove a bearing, you know that a press fit can be a good way of joining a shaft, especially if it's a driven shaft and is fixed at the other end, so that you don't require any locating features and you have the bearing that's grounded. It's a good way. Shrink fits are where we heat up the hub, so you make the hub really hot. Obviously, you don't want to change the crystal structure of the metal, the phase structure of the metal, but you heat it up, you get thermal expansion of the hub. You can even have the shaft and you can cool it down or leave it in a freezer and then put them together, and then they'll be then when you put them together and they equalize, then they also have a press fit. So we have a question: transmitting torque, what's more effective, a spline or an aggressive press fit? The spline is better. Okay, so you're not going to see a press fit, for example, on a car driving a wheel. Okay, you would see a spline so that you could transmit more torque. So that's the answer to that. So higher torques are better done with splines. So when you use an interference fit, because you're causing two materials to interfere with each other, you're obviously going to get stress. That stress could cause other problems, which we haven't discussed, which is related to the surface failure lecture. That is actually uploaded to my site, and you also have a video of that from Norton, but we haven't discussed it just yet. But you can get fretting failure or corrosive fretting between the hub and the shaft when those two materials are rubbing against each other. They can cause surface cracks. So there's something called the rule of thousandths, and the rule of thousandths says you want to be 1,000. I'm not talking about inches. I'm saying thousandths. So 1,000th. So you want to be 1 to 2,000th units of interference per unit diameter. Okay, so these are not inches. These are any units. Okay. Larger diameters use a 2,000ths rule, and smaller diameters use a 1,000ths rule. These are not necessarily in inches. Okay, so if you have metrics, it's just, you want the interference to be between 1 to 2 thousandths of the diameter. For example, if we have a 2-inch diameter shaft, then we would want to have 4,000th of an inch of interference because it would be larger diameter to use the 2,000ths. Okay, between large diameter and small diameter, you can say that diameters up to 1 inch, you can use the 1,000th of an inch. This is the machinist rule of thumb, which is different than the rule of thousandths, even though they have the same interpretation for some lengths. But the machinist rule of thumb, if you're going to use a press fit, is 1,000th of an inch of interference, not clearance, interference, up to 1 inch diameter shaft, and 2,000ths of an inch for diameters from 2 to 4 inches in diameter. So for these, you also are going to have stress concentrations, and those are going to range from 1 to 2. We can use the thick wall cylinder stress calculations that were derived for the pressure vessels from statics. If we do that, we can calculate the pressure that is due to the press fit. We have this variable delta here, and it's expressed in terms of delta. That delta is 2 times the interference. Okay, so the delta R is this guy up here. If you see this picture, that delta R is the interference. Okay, so twice the interference over this expression here, where we have the inner and outer diameters. I'm sorry, inner and outer radii. The allowable torque, then, it can be expressed in terms of this pressure term here, which is the force times the area, or the pressure times the area times the length of the shaft. And we can rewrite that torque and find the torque that we're able to transmit through here. This mu is the friction coefficient, and so this allows us to express a interference fit in terms of the torque that it can withstand without slipping. Okay, and obviously you're making assumptions that the surfaces are perfect, that the tolerances are perfect, that you don't have oxidation, etc. Okay, so you probably use this and then relax it a little bit. We can also look at the stresses in the shaft according to the pressure and the stresses in the hub, and we have a tangential stress and we have a radial stress. Okay, and these are those values that you can calculate. Now, there's a lot more information pretty much for every machine design element that we go over in handbooks such as Mark's Mechanical Handbook or the Machinery Handbook, but this is a good place to start. All right, so now we're going to talk about flywheels. And so a flywheel is something that stores energy. Okay, flywheels are used to store energy. They're also used to smooth out speed variations due to torque fluctuations. Okay, so you can imagine here if you have a motor, okay, and that motor is applying some torque, and that torque is being transmitted through a shaft. If over here you have the torque of the load or whatever you're trying to drive, and that torque varies over time, you don't necessarily want that torque to be reflected into the motor. Okay, so if you're a little clever and you suspect you're going to have a time varying torque, you don't want it to negatively affect the speed. And then let's say you had ample torque for the load and to run the flywheel, you can add a flywheel. And that flywheel inertia is going to store energy. And so if this torque wants to slow down, we have all this energy that's spinning and it wants to keep on rotating, and it causes this torque to it applies a reverse acting torque to kind of neutralize it. The same thing is true if the load suddenly decreases and we end up applying a negative torque because the flywheel is going like this. That negative torque, then the torque that's applied to the motor doesn't have to spin the whole flywheel and the load, and so it's easier to spin the flywheel. So the flywheel stores energy. We can express that energy in terms of the kinetic energy. We know it like as 1/2 mv squared for point masses. For rotating things, it's 1/2 I omega squared. In this case, this would be the motor shaft and everything that's rotating that would be in this moment of inertia term. We can express the moment of inertia of the flywheel. Okay, if we know the inner and outer radii, we can just say for a disk it's 1/2 mr squared, or in this case we have both the flywheel and the rod in there. We can calculate the mass. The mass is actually going to be just the weight of gravity, and in this case we can introduce the density of the material and calculate the actual mass based upon a certain thickness of the flywheel. Okay, so this is just the density of the material. It's just pi r squared times t times the density of the material. So it's the volume times the density gives you the mass. All right, so if we want to design a flywheel, we want to basically pick the flywheel geometry. And we want to pick that geometry based upon what we consider a maximum deviation from the average speed. Okay, and the way that we find that moment of inertia is, well, we have to find out the amount of energy that we want to smooth, and I'll show you how to do that. So the analysis goes like this. We know that the sum of torques is equal to I alpha. That's the same thing as Newton's law when we multiply both sides of Newton's law by the radius, right? So the force times the radius is the torque. and the mass times the acceleration. In this case, you'd have m times r alpha, which is that. So if we have the applied torque and we have the mass moment of inertia, this is just Newton's law expressed in torque, then we can rewrite that as the sum of torques is the torque of the load minus the torque of the motor, and that's equal to the shaft inertia times the angular acceleration. Well, if we say that the torque that's supplied by the motor is actually the average torque, then we can rewrite this in terms of the average torque. And we just say, well, the torque of the load minus the average torque is I alpha. Okay, alpha is the change in speed with respect to time. If we multiply that by d theta over d theta, which is the same thing as multiplying by 1, then we can rewrite this as d theta dt, which is d d theta dt, which is omega, and then we have d omega over d theta, and then we can move the d theta over here and integrate. If we rewrite that alpha in terms of d omega over d theta times omega, then we get this expression where this is the load torque, or the torque applied by the load. This is the average torque that we say is supplied by the motor. And then this is the motor inertia times omega d omega d theta. If we multiply both sides by d theta, then we can get an expression that's easy to integrate. Okay, and so we get an expression here that shows us the relationship between the change in energy stored in the flywheel, which is the torque times the radial deflection, and we see that it's equal to the change in the kinetic energy. Okay, this is actually the right-hand system, the right-hand side. This is the left-hand side. I got these backwards. Okay, but I omega squared, or I delta omega squared, is the change in energy, and this is the stored energy, which is essentially just like the force times the distance integrated. Okay, so in summary, we have an expression then that we can use to express the energy stored in the flywheel as related to the variation in the speeds between the min and max speeds. All right. And so what's done in practice is we want to minimize the fluctuation of the speed in the shaft. Okay, and we'll just say the fluctuation is the max minus the min speed. And we want to normalize that by introducing a coefficient of fluctuation. Okay, so if the max minus the min speed is equal to the average, or if they're the same, if the max speed is equal to the min speed, then it's 0. If the max minus the min is 1% to 5%, that would be a coefficient of fluctuation that we would want for, say, a precision machine. If we have a crushing machine where we have a flywheel that has to store a lot of energy and then release a lot of the energy, we may make this much larger, and that would be about 0.2. So these are some ranges that you can use. Now, if we take what we showed earlier as that right-hand side equation where we have the energy, the kinetic energy stored in the flywheel, we can expand that out. Okay, so we just basically expand the second term here. When we do that, we get an expression, omega max plus omega min over 2, and that's the same thing as the average angular speed, which we can plug back in, and we can plug it back in the coefficient of fluctuation. So if we do that, then we can actually get an expression for the energy stored in the flywheel as a function of the average, the desired average angular velocity of that flywheel. Okay, so when we multiply it out, then we can solve for the inertia that we want to store in the flywheel. That is the design process. So at the end of the day, we want to design the flywheel such that its moment of inertia is equal to this value, okay, where we have the stored kinetic energy over the coefficient of fluctuation over the average desired speed. If we don't know this number, you can actually put a load cell or put a torque load cell in line with the shaft and run the machine, and you'll get a curve like this. Okay, so this is the torque over time, and so we could find this by instrumenting a shaft with a torque load cell. They're readily available. You can get them for $1,000 to $2,000, and then you have to get an amplifier, and then you collect the data. But it's if you're doing an engineering design, you may want to do that. Okay, and then you can actually get this these torque fluctuations over time. Okay, so if you take the torque over time and you integrate that, that's equal to the energy that is stored that is stored in the energy, that the fluctuating energy, excuse me. Okay, so if we integrate this curve, the torque over time, well, that is the energy that we would like to dissipate. Okay, so this is an example of the same application where we took went through this process and then designed a flywheel to kill this energy, this amount of energy. Okay, and this is what it looks like after it. So before, okay, this is at a desired value of torque of about 7,000 up here, but the torque fluctuations went all the way up to 34,000. Okay, I don't know what the units are, but probably inch pounds or newton meters. But the point is, after we added the flywheel, you can see the torque fluctuations were dramatically diminished. So pause here for a second and see if you have any questions. I'm going to drink some water because I know my voice is probably, you could probably hear my dry voice. All right, so maybe you're already on your email or watching another YouTube video and trying to listen, or you don't see my text, or you have no questions, so we'll go with that. All right. So most people might say that the max stress of a flywheel is actually on the outside radius because it's spinning the fastest, or it's it's far enough away, or it has all the material behind them. It's actually not true. Okay, when the flywheel spins, all of that material is trying to pull that material underneath it away. Okay, and that acts like internal stress. Okay, and we can actually calculate that. So we can calculate the tangential and radial stresses for a flywheel. But if your flywheel is moving too fast, okay, you see this omega term, omega squared. Okay, so if you accidentally put 10 times the speed that you want, you're going to get 100 times the stress. Okay, hopefully everybody sees that. This is how you can calculate that from a flywheel with just a disc on a shaft. This is your tangential and this is your radial stresses. These are your tangential stresses. Okay, they obviously don't. I mean, this would be reflected on each side. Okay, but this is your stress as a function of the radius. This is your tangential stress here. Okay. So the max stress is due to your tangential stress, typically, and that is on the inside of the flywheel. You do not want to have something spinning, at 20,000 RPM and then fail from the inside out. So if the flywheel runs at a constant speed, then it's reasonable to treat this as a static stress and do the static stress analysis. If your flywheel or your application is starting and stopping a lot, then you got to calculate that tangential stress, and you need to account for fatigue. Obviously, it's unlikely that you'll have your motor starting and stopping on the order of 10 to the 8 like we do for some of the fatigue life, or 10 to the 6 revolutions like we do for the high cycle fatigue. And so you may have to use a low cycle fatigue strain-based analysis to evaluate that. All right. Any questions? Okay. So there's two more things that I want to talk about, and that is critical speed of shafts. And when we say speed, we're talking about the critical RPMs of the shaft, or the critical radians per second of the shaft. And it's important that we avoid running a system for the so sorry, I lost my train of thought trying to read the chat and talk at the same time. Okay, so we're talking about the critical speed of shafts. When we say speed of shafts, we're talking about how fast they're spinning. Okay, now this is obviously not a shaft, but it's an example. You've probably seen it in your modeling class 100 times, and it is your physical mechanical model. Okay, well, it turns out that every physical mechanical system is made up of mass, has some inherent damping and stiffness. Okay, even if you have a block of aluminum and you hit it with a hammer, okay, it has a stiffness and it has damping. Although the damping is very low, it has some internal damping due to the internal energy dissipation from the relative displacement of the atoms in the crystalline lattice of the metal. The point is, you have a physical system, you have mass, stiffness, and damping. Now, in your modeling class, what we did is we treated it as a mass spring damper. So you may remember this: if we have some forcing function on some mass with some damping and some stiffness, and we pull the system, that we can model this system using this differential equation. We can take the Laplace transform of this system, and if we assume zero initial conditions, we can get a relationship between the displacement and the applied force that tells us the transfer function, or the transfer between applied force and displacement. We don't always like these units, though, and so we rewrite this often as a generalized second order system where we divide the numerator and denominator by the mass, okay, and we call this term over here at this term on the bottom, we call it the natural frequency squared. Okay, and if we do that, then we say, well, the natural frequency is the square root of k over m. Now, the reason this is important is because we are saying that the natural frequency of a system is defined by the system's ratio, the square root of the system's ratio of its stiffness, okay, over its mass. That's the natural frequency. So you might say, well, what about the damping? Well, the damping doesn't make the natural frequency different, okay? It just tells us how bad the thing is going to oscillate, okay? If we have less damping, obviously it's going to oscillate higher with larger amplitudes with no damping. But the natural frequency, the way to think of it is it's the stiffness over the mass. So this way of doing analysis, these are linear constant coefficient differential equations. We assume zero initial conditions, and we could do this nice little analysis so we could define things in terms of variables like the natural frequency, and we could do all sorts of other stuff with that. This way of modeling is called a lumped parameter system, where we lump the mass, stiffness, and damping into these discrete terms. We lump the mass, we lump the stiffness, and we lump the damping. Okay, obviously the spring has mass. Obviously the damper has mass. Okay, but we kind of ignore that. And we treat this as a lumped parameter system, and it works. Okay, so it's been said that all models are wrong, some work, and this model works. But what do we do when we have a shaft system? Okay, well, it turns out that, well, we can kind of treat this as mass 1, this is mass 2, this is mass 3, this is mass 4, this is mass 5, and go on from there. So continuous systems such as shafts, they can be thought of as infinite number of lumped parameter systems. Okay, and that's similar to how finite elements work, but not exactly. What that means, though, is if we treat these as each different masses, okay, then each one of these are going to have their own natural frequency. In this case, since we have this is a shaft, and often the loads are applied in torque, we're going to have 3 different modes of vibration, which we'll get into. But because this is not just a simple mass spring damper system, but it's a continuous mass system that has inherent damping and inherent stiffness, it'll have an infinite number of natural frequencies for this system. So when you build a machine, you are building into it the natural frequencies of the machine. Okay, so the only way to change the natural frequencies are to change your machine, to change your geometry. Okay, but we are primarily concerned for most all machines with the lowest natural frequency, or what's called the fundamental frequency. Okay, so when a system is driven either by an applied torque or external forcing function or environmental forces or whatever, or self-excitation, okay, and self-excitation can happen if, like, you had a chip in your mass that's rotating around the gear. So then you get an imbalance in mass, and then you get a time-varying torque, and that causes the thing to swirl. We'll talk about that. Okay, so when a system is driven either by self-excitation or external excitation at its natural frequency, that causes the system to resonate. Okay, we already said that. So when you operate a machine, you do not want to operate at the natural frequencies. Okay, you do not want to be anywhere close to them, because you can have catastrophic failure, premature wear, etc. Okay, so this is an example of different response curves based on different damping. Okay, so the less damping you have in your system, the less energy losses you're going to have due to frictional losses. Okay, so damping is often something that involves friction, and even though you may think damping may be desirable, you don't want to have a brake, running on your rotor the whole time you're driving it down the road. Okay, so you want to, in general, you'd like to keep your damping balanced if you have rotating machinery, and in fact very low if you have rotating machinery. But if you operate a system, and this is the example of this system that we talked about, this is just a single degree of freedom lumped parameter system. This is just to highlight the concept. This is not for shafts. Okay. This shows what happens if we drive the forcing frequency at the natural frequency. We're over here at 1, and if we have low damping, then the amplitude of the output explodes. In fact, if the damping's 0, it goes to infinity. Okay, so you do not want to operate at the natural frequency of a system. Okay, so you would not want to force your system here with this forcing function F. You would not want to apply an F into the force into the system at the same frequency as omega if you have very low damping, because then you get crazy output in X for the X amplitude, and you'll cause problems in your machine. If your machine is not driven with the same amplitude, the input-output amplitude, but instead it's subjected to self-excitation, okay, so that's if the machine is actually subject to, say, I guess, its own structural self-excitation. And you can also get a machine that can have its own self-excitation. So natural frequencies, it's bad if you drive it at its natural frequency. It's also bad if it or the environment drives it at the natural frequency. Okay, so we got a question. I've always been confused about how natural frequencies of rotating systems are damaging. Okay, is the wear per damage caused by the mass imbalances? So that's a good question. So the reason you don't want to do that is for the simple case right here, right? So let's say you have a forcing function and you force this system at its natural frequency. Well, this is the ratio of the output of the system to the input of the system. Okay, so that means if you put an input of like 1 into the system, you're going to get an output of 6 if you have low damping, or you get an output of 5 times. So usually you'll put an input in close to what you want the output to be. Okay, but in this case, it blows up at the natural frequency. And so driving a system at its natural frequency, another way of saying it for mechanical systems, if you're giving it an excitation at its natural frequency, you're going to cause the displacement of the system to explode. Okay? Mathematically, if you have 0 damping, it's a divide by 0. It goes to infinity. Okay? And it's not where you want to be. Okay? So there's 3 natural frequencies to be concerned about. Okay, so the first one is torsional. Okay, I turned this sideways so that's like a shaft, but you get, if you have some oscillation here, then it can rotate about the disc, about the axis. That's the torsional vibration. You can have lateral vibration, and that lateral vibration is due to vibration input. So if you have some vibration, if you're shaking a system, you can excite the system at its natural frequency. You can also have swirl. Okay, so let's say you put some big mass on your system and you caused it to deflect, making it a little eccentric. Well, then when it comes and spins, it's going to spin around that axis. It's going to show up on the other side. Okay, and then you're going to get that thing to swirl around the axis. Okay, so if you, we'll talk about each one of these. All right, so usually, like if you have a complex system, you're going to use FEA. You're going to put the masses and everything on there, and then you're going to take a look at, the deflections. Before you had these tools available to you, people actually had to do the back of the envelope calculations, the analysis, and you can still do that today pretty simply by using Rayleigh's method, and it's actually accurate within a reasonable percentage, a few percent. Okay, and this approach is similar to how we did the design for the flywheel. And this approach is we basically can equate the stored potential energy, the strain energy, to the energies to the maximum velocity. Now, just like other design problems that can be really frustrating, you don't know what the deflection is going to be before you do the design. Okay, so how are you going to get your natural frequencies? Well, you can guess what they're going to be based on experience or based upon a simplified case. Okay, so if you don't want to go through all the geometry and the definition, I mean, you can put a shaft in SolidWorks and throw some masses on there and then apply a load of what you think it'll be, apply properties for for a certain material that you're going to use, and then do the static analysis. Okay, and then look at those deflections. Okay, so like for example, in this case where we have 3 different masses, you can model that up in SolidWorks pretty quickly, and you can get estimates for the deflections, or you can use the singularity functions, write yourself a little program, and then get the deflections from there. And then what you can do is you can say, well, the energy, okay, the potential energy of the system is going to be the 1/2 the mass times the gravity. So mg is a weight, that's a force, times the distance, and you can use the different distances. Okay, so this is force times distance here. Okay, and that's your stored energy. And then you can say your kinetic energy is omega n squared times the mass times the deflection. Okay, and that's the kinetic energy that's in the system. Okay, and it has the same units like the 1/2 mr squared. Well, that's I, right? So that's I omega squared. That's the kinetic energy stored in a rotating disk. So what's good about this is then now we have an expression for omega n squared that we can find if we set them equal to each other. Okay, so we say that EK is EP, or omega n squared is equal to this term up here. If we do that, we can solve for omega n. And then we can express it here in terms of just the individual masses and the deflections of those masses. And if we write it out, we can actually express it in terms of the gravity times the individual weights of the different components and their displacements. And we can get an estimate of the natural frequency for a system based upon those deflections. And it's said that it's within a few % of the natural frequency. Well, why do you want to know that? Again, if you're going to run a motor at a certain RPM, okay, and that RPM, when you convert it to radians per second, if it is close to this value, you need to redesign your system because you are going to cause problems. Okay, so I hope that's clear. Okay, so that is the lateral vibration. Okay, so that's this case here. That's the lateral vibration. Okay. We can also have shaft whirl. Okay, so if we apply a mass onto a shaft and it deflects, then it's going to come down here, and then when we spin it, okay, it's going to come all the way around. Okay, so we're going to have this shaft whirl. Okay, and in this case, we do something similar where we say that the stored energy, which is the force times the distance, is equal to mv squared. Okay. And in this case, we have this distance here times omega squared. And so we can equate the stored energy, which is the left-hand side, with the kinetic energy, and we can get an expression for how far down it's going to go, or we can get an expression for the deflection over the eccentricity in terms of the natural frequencies. Okay. This happens when we have masses that are not perfectly distributed around the center of the axis. Okay. So when we have a mass that's not centered around the center of the axis, that's when we get this. And what's interesting about this, we have this 1 minus term. Okay, so when we cross over a natural frequency, it actually starts going the other way. Okay, so we get a 180-degree phase shift. So it'll be going like this. Okay, and then you pass through the natural frequency, it'll go the other way. So yeah, if you get a natural frequency, you get that phase change. This is just the torsional vibration where we have the omega is square root of k over Im. We have the stiffness that we defined earlier. This is the polar moment of inertia for a circular cross section, the moment of inertia for a circular shaft, and this is the effective polar moment inertia if we have more than one shaft on there. And using those values of KT and IM, we can actually calculate the natural frequency for a mass rotating around a disk. Okay. So if we want to consider the natural frequency of 2 disks on a shaft, we can do that by finding this location here. Okay. And that location is going to be the location where the natural frequencies of these two are the same. All right, and that's going to be the natural frequency of oscillation. And if you do this, you can solve for that location, and then you can use that location to find the natural frequency of that system in terms of the stiffness of that system and the inertias, the moment of inertia for both disks. If you have 3 masses, you can use this equation here. Okay, so last thing I want to do, and I know that we're already a few minutes over, but if you'll bear with me, I just want to show you a couple pictures, and those are couplings. Okay, so we use 2 different main types of couplings. They can be separated into rigid couplings and flexible couplings. These are pictures of rigid couplings. Rigid couplings, the point is to fix the shaft perfectly, clamp it down, and try to just get the shaft to be as one uniform piece of material. Okay, so these are widely used. Obviously, the friction has to be high enough so that it doesn't slip. This is another type of rigid coupling, and that's where you use keyways on the inside of the hubs. Okay, you face them towards each other so they can't get out, and then you lock them together. So this is a shaft that's coupled, and you're using these tapered keyways to smash into there, and you can actually have the key go through the material as well, or you can just have it to where as you tighten it, it goes up the ramp, increases the compressive forces of that. Okay, we also have compliant couplings, and compliant couplings are designed based on their application. Which is to deal with axial misalignment, angular misalignment, parallel misalignment, and torsional misalignment. Okay, and so these are the different types, and this is my last slide. But you can have jaw, flexible disc, gear spline, helical, metal bellows, Schmidt offset, and hooks. I've seen an awful lot of these, and I've seen an awful lot of these for like small stepper motor applications. And I've seen these on some bigger, slower moving machines. But here are the different compliant couplings. They have their different benefits. Okay, so if you don't have a perfect alignment of the shaft, okay, this tells you, this is a guide to help you pick which shaft coupling you would use, which compliant coupling, if you have this type of misalignment. Okay, so you can have axial, angular, parallel, and torsional misalignments. That's what we showed here. So those are those 4 types of misalignments. And based upon those, that's what you could do. So if you only have axial misalignment, okay, then you can use a rigid coupling. Okay, that's what we saw first. If you have a small bit of axial, small bit of angular, less than 2 degrees, and a slight parallel misalignment, and a moderate torsional misalignment, then you can use a jaw type coupling. Okay, and so this allows you to transmit torque through a system where you have some misalignment issues. So I won't read the rest of them. You can look at them. This is a guide. You just need to be aware that if you're designing a machine and you have to transmit torque and you have some misalignment, then you probably don't want to use a rigid coupling. You probably want to use a compliant coupling, but there's the sacrifices. You're not going to have the ability in general to transmit the same amount of load. So we'll end there. Are there any questions? I appreciate you guys staying with me to the end. I'm sorry I went a little bit over. So are there any questions? So there's a question. You need an imbalance or input to excite the system at the natural frequency, right? So the first question is, do you need, and I'll go ahead and go over to the webcam. All right, so your question is, do you have to have an imbalance in your system or an excitation frequency? Yes, or you could have a self-excited system. Or a system that's excited by the environment. A self-excited system would be a system that has a torsional imbalance, for example, in the rotary shafts. Okay, and so the system itself, by spinning, is exciting its own self. So if you have ever had an old ceiling fan and maybe you had a pillow fight and a pillow damaged one of the blades or bent it, then you get an unequal torque input into the system, and then your fan starts to go all crazy. That would be a self-excited imbalance. You're operating too close to the frequency of the fan that's going back and forth. And so you'd want to deal with that by adding a mass. And if you get a new fan, you usually get these little wedges or stickers. You can put them on the top and try to balance it. If you have a forcing function, or if you're running at a certain speed and that speed happens to be the first fundamental frequency of the shaft torsional mode or the shaft transverse mode, then you're going to cause troubles there because you're exciting it at its natural frequency. Okay, so it's can often illustrate it with the slinky. So if you've ever had a slinky, when I was a kid, that was something that I wanted, and then we got some. So if you move real slow, then the slinky moves with you, okay? So this is the input, this is the output. So if you move the slinky real slow, then they're in line with each other, they're in phase with each other. So then if you try to change the frequency of the input, then the bottom of the slinky will change based upon that forcing frequency. Even though the displacement amplitude is the same, I get a different output. And if I go at the natural frequency, I can get that slinky to go, totally crazy, And then if I go really fast, then the slinky dies back down, okay? So that at that place right there where you're operating at the natural frequency and you get this crazy oscillation, that's the natural frequency. So if you go lower than that, then it moves in line. And if you go way higher than that, it settles out or doesn't even move. Okay? And there's classes that deal with that. I teach a class in dynamical systems, signal processing, and the art of controlling machines, and we cover topics like that in that class. So Michael's asked a question, can you go back over how you find the stress concentration for keys? Okay, good. All right, so let's go back. Stress concentration for keys. So I didn't put all the information here. For the other one, but basically we're looking at the corner radius, the corner radii. That's your R here, and your D is your diameter of your shaft. Okay. And if your R over D has a ratio of, for example, close to 0.02, and then your stress concentration factor is going to be over double than what you thought it is. Okay. That's your stress concentration. That's your axial stress concentration and tension. This is your stress concentration and shear. Okay. So this is like your nominal stress concentration. This is without a key, no key right here. And then this is with a key in place that's transmitting torque. Okay, because you're subject to shear. So like I was saying before, stress concentration is going to be 2 to 4. So if you're over here, you're already at 3 to 4. If you have a small radius, if you have larger radii versus the diameter, then you're going to get lower stress concentrations. Okay. So there's different ways that these are made. Okay, so this is a end milled keyway. So you would come in with a milling cutter, and then you just go, and mill out the axis. That might be a pre-hardened material that would get hardened later, or a steel that's soft enough to machine, and you would mill that out and leave the keyway. So that's a double-ended keyway. This is a single-ended keyway where you only have the stress concentrations here on this end. And then this is a sled runner keyway, and that reduces the stress because this looks like a sled. Okay, and then you would basically just take the diameter of that radius. The radius of that corner inside of the keyway and divide it by the diameter. Does that answer your question? Oh, this this picture is actually in the chapter. It's in chapter 10. But the point is, it's like, pretty much if you calculate your stress, if you look at the stress concentration vectors, in general, you want to maximize your radii. Okay, your edges. You don't want to have any sharp corners anywhere if you can avoid it. But if you do have corners, okay, then the stress concentration, I think the highest stress concentration, even in the back of the book, I think they approach 5. So if you multiply your stress by 5 in your application, and you make sure you don't have any sharp corners, and your design meets the objectives, and you don't really need to change or have to change your cross-sectional areas or whatever, then it's something to be aware of. Okay, you just got to be aware of these stress concentrations. You can't design machines that are going to fail in fatigue, okay, because we know that it's like over 90% of the failed parts. So you don't want to do that. All right. All right, are there any other questions? All right, so I don't see any other questions, so thank you for your attention, and we'll go ahead and end here. And I'll send an update about the presentations. The homework and the presentations will be delayed to Wednesday. Thanks.